So just a minute. So hopefully today we'll be able to complete the syllabus for the class test. But yeah, I'll be a little fast. Today we'll talk about transformations of random variables and how to find the probability density function or distribution function corresponding to functions of random variables. We talked about that maybe informally for certain cases, special cases, but now today we'll formally introduce that and we'll talk about the techniques, how to do. Hopefully we'll be able to finish it today. Yeah, so and this is a part of the syllabus of this exam next week. So what? So this is functions of random variables. So the idea here is, okay, suppose you are supplied with some random variables x2, x1, dot xn. Okay, and suppose you also know, let's say, okay, here mainly we'll be focusing on one random variable or two random variables, but it can be in general any finite number of random variables. And suppose what is given is suppose we know the joint probability density function or distribution function. Suppose we know the joint probability distribution. I mean, if it is more than one random variable, suppose we know the joint probability distribution, or let's say a density function of these random variables, and then the question here is, suppose we want to calculate. So we can define a new random variable. Let's say y, which is a function of, let's some u function of this x1, x2, xn, and then what will be the PDF or probability distribution function or the density function of y. So that's the question here. So what is the PDF of y? And this could be any function, but actually we'll focus on a very particular set of functions. In general, it can be anything, but if it is anything, there is no general technique to find the PDF of this function y. So, so what we'll discuss is we'll discuss two methods to calculate the PDF of y. One is called, so there are many methods, but we'll basically discuss these two methods. One is which is called distribution function technique. Distribution function technique. And another one is called a transformation technique. Transformation technique. Yes, but the question is which one is preferable? So it depends on particular problem. Okay, so like which one we should use, for a given particular kind of a function. But yeah, so in some cases, for example, if you have a single random variable, this is generally people use, and for more than one random variable, this is what people generally use. But sometimes you need not also use this for I mean, it depends on the problem. So there is no general rule like which kind of technique you should use or method you should use to calculate the PDF or the probability density function for this function of the random variables. Okay. So what is this method? The first method, let us first discuss the first method, which is distribution function technique. Distribution function technique. In fact, for discrete problem, this is not very this is not very difficult in most of the situations. That's what people talk about this function when the given random variables are continuous, not discrete. Okay, so in this case, in this particular method, we first find out what is called the probability distribution function, which is fy, which is p of, let's say, p of y is equal to p of y is equal to some small y, which is according to the definition. So this will be probability of this function of x1, x2, xn, whatever it is equal to y. So once we find that distribution function, then we take a derivative of this and then find, so then differentiating fy, okay, we obtain the PDF, which is fy, which is dfy dy. So I'll give you some examples, and through examples we can understand how it does it work. So my first example is like this. Suppose x is a random variable, and the PDF probability density function of, so here I have just only one random variable, and suppose PDF of x, this random variable is given by this. So let's say 6x1 minus x when 0 less than x less than 1, and otherwise it is 0. Okay, now suppose I want to find the PDF of y, which is a function of x, let's say x cubed. So what do we do? So we'll first let's say gy denote the probability distribution function of y. So this is probability of y less equal to y for any y, small y. So essentially this means probability of x cubed less equal to y, which means probability of x less equal to y cube 1 by 3 cube root of 3. And now we can use the probability density function or distribution function of x, and then we can find it out. So it will be nothing but 0 to y to the power 1 by 3 fx dx. Fx here is 6x 1 minus x dx. So 0 to 1, and here is 0 to y to the power 1 by 3, whatever the value of y is. And so this will be 3y to the power 2 by 3 minus 2y. So therefore we can say that gy, the PDF of y, is equal to 2y to the power minus 1/3 minus 1 when 0 less than y less than 1 and 0 otherwise. So this is typically yeah. So this is how we'll proceed when we have this distribution technique. Okay, so first we'll function the distribution function and then we'll take a derivative. Another example, let's say another example. I mean, these are the famous examples you could say. Another example is suppose x is any distribution function, any PDF, any random variable. Okay, x is any random variable, and suppose, okay, I want to find out, okay, y, which is one PDF of y in terms of PDF of x, but y is, let's say, function of x, which is mod x. So how do we go about it? Okay, so if I in specifically, let's say, okay, we can pick a particular random variable x, which is this, let's say x is normal, let's say x is standard normal, let's say standard normal, let's say, and then the question will be, what is the PDF of if x is standard normal, then what is the PDF of y? So in general, let us find out it in general, and then we'll see what happens if x is standard normal, then what will happen. Okay, so if I use the technique, so the probability distribution function will be probability of y less equal to small y, which means probability of mod x less equal to small y, and so this will be probability of minus y less equal to capital X less equal to small y, and this will be nothing but fy minus f of minus y. Now if we take the derivative, okay, then upon differentiation, what you can say is, let's say gy period, so this will be fy small fy, the PDF of this, plus f of minus of fy. Now see, now what happens here is this value y is let's say is always positive, right? So whatever be the value of x is, doesn't matter, small x is, let's say small y is always positive. So since mod x, okay, is non-negative, okay, then we can say that g of y, okay, z of y is equal to 0 when y is less than 0, and we can also assume that this is less equal to 0. So then we can say like, okay, so gy is nothing but fy plus of f of minus y when y is bigger than 0 and 0 otherwise. So this is just for any general x. Okay, if I know the PDF of x, the random variable x, then I can find out the PDF of y, which is nothing but this fy plus minus fy when y is bigger than 0 and 0 otherwise. Now, if x is normal, standard normal, let's say, so then if x is standard normal, then that means x distributed is n0, 1. So then what is gy? So gy will be then n, okay, y 0, 1, like 0, 1 are the mu and the sigma. So then this one plus n, okay, minus y, okay, 0, 1. So but it's a symmetric about 0, so it is nothing but 2 times n y 0, 1. So yeah, so it is normal, but it is just a 2 times the normal. So this is you can say this is an example of a function of a random variable. This is how we can find it out. So this when y is bigger than 0, and otherwise gy equal to 0. So this is an example of the PDF of y. Let's see another example, which is a function of two variables. Okay, let us say let the joint PDF of, let's say, two random variables like x1 and x2, okay, be something like f of x1, x2 in that case, f1, x2. So this will be 6 e to the power minus 3, let's say x1 minus 2x2. When let's say x is bigger than 0, or x1 is bigger than 0, x2 is also bigger than 0, and let's say 0 otherwise. So then suppose the question is find the PDF of y, which is a function of x1 and x2. So let's say it is x1 plus x2. This is what we are going to find out. Okay, so yeah, so then what we can do is using this technique, we can just say, so set here it means y is equal to x1 plus x2, and where we use the joint distribution to find out the PDF of this y. Now, yeah, so fy, if we write fy, then we can say this will nothing but 0 to y, and then we can write, because y equal to x1 plus x2, we can write 0 to 1 minus x2, and whatever y is, doesn't matter. So this is now f of x1 x2 dx1 dx2. So it is 6 e to the power minus 3x1 minus 2x2 dx1 dx2. And if you just integrate it, you will get the value 1 plus 2 e to the power minus 3y minus 3 e to the power minus 2y. And that is how we can now differentiate this. Okay, now then differentiating upon differentiation, what we can have is fy. So you have to take a derivative with respect to y. So this will be df y dy, and this will be then 6 e to the power minus 2y minus e to the power minus 3y when y is bigger than 0. Otherwise fy is equal to 0. Okay, so these are typical examples, and you can just find out, okay, the PDF of a function y, okay, I mean PDF of a random variable y when y is a function of a given random variable. You directly just calculate its polar distribution function and then take a derivative. Okay, this is standard technique. Okay, and sometimes what will happen is this will be a little bit complicated. Okay, or maybe derivative does not exist. So then you have to look for other methods to calculate the PDF of the function of this random variable. So this is, and now we'll talk about the transformation technique. And here we'll discuss in two cases. So first of all, let's say is about the univariate case. So let us say one variable. So it is just you are given a random variable x. So here x is given, or you know the PDF of x. We know. Then the question is we find PDF of y, and which is a function of x, so some u of x. Now I'll just show you an example that this could be really easy sometimes. So when you have a discrete random variable, x is discrete. Okay, so let us see an example here. Suppose x is a random variable. Okay, suppose x denotes the number of heads. Okay, heads in 4 tosses of a balanced coin. 4 tosses of a balanced coin. This is what is given. Then the question is find the PDF of y, which is equal to 1 by 1 plus x. Okay, now here you see, okay, so since x is number of heads, so this is like binomial distribution, right? So x follows binomial distribution, and S is binomial when n is equal to 1 by 4, n is equal to 4, and it is a balanced coin, so it's n equal to 4, and probability it is a balanced coin, so it is half, and 4 times you are tossing the coin, so you can find out. So then what is the PDF of x? Okay, so the PDF of x will be, so this is x could be number of heads could be 0 or 1 or 2 or 3 or 4. So then probability of number of heads, which is 0, will be 1 by, you can find out the distribution of this, and you can calculate that this will be 1 by 16. And then for 1, when number of success k is equal to 1, let's say. Just a minute, guys, somebody is knocking at my door. Yeah, so if we just use the binomial distribution, then I can find out this probability. So here k is the number of success, let's say. So if you do that, putting k equal to 2, you know it is 6 by 16. Okay, 6 by 16. Then for 3 it will be 4 by 16, and for 4 it will be this. Now say if you want to find out y, which is let's say 1 by 1 plus x, then what happens? 1 by 1 plus x, then basically we are saying this value of y is equal to 1 by 1 plus small x. So now x could be, I know, 0, 1, 2, 3. So then basically what we want to find out is when x is 0, then y is 1. When x is 1, then this is half. Otherwise 1 by 3, 1 by 4, 1 by 5. So this is y, and I want to find out what is g of y. Now see, since this is the 1-1 correspondence, okay, so we want to substitute directly the binary distribution when n equal to 4 and p equal to 1 by 3, and then here this means x equal to 1 by y minus 1 for x. So basically, if you had this fx, which is equal to 4cx 1 by 2 to the power 4, okay, when x equal to 0, 1, 2, 3, 4. So basically gy will be nothing but f of 1 by y minus 1. So this will be 4 1 by y minus 1, and then half to the power 4. So when y is equal to 1 half 1 3 1 by 4 and 1 by 5. So then accordingly you can put the value of y and then find out that gy would be nothing but 1 by 16, 4 by 16, 6 by 16, uh, 4 by 16, and 1 by 16. So this is the case. Now you see here this x and y, this PDF, okay, that does not change. It is the same PDF. Okay. So what happens is if this is 1 to 1, 1 to 1 means one for any x value, this y value is unique, or for any y, this is 1. So that means if this function is 1 to 1, in most of the cases, what we'll get is there will be no change of this distribution function. Okay, I mean, you will always get that because so the same what probability of fx equal to x is same as probability of fy is equal to y. So there is, because this is a one-to-one relationship. So that's why you always get the same distribution function back, PDF function back. Okay, probability distribution function back. So there is no change. But the change will be there when this function is not 1, 1, let's say. For example, I mean, if I just change this function, okay, let's say this is yeah, instead of y equal to 1 plus x, okay, suppose I ask you to find the PDF of some other random variable z, which is, let's say, x minus 2 whole square. Okay, and then you will see this function is not 1, 1, but different values of x you can get the same z. So then this distribution function will change. So then for suppose you want to find out the PDF of z, suppose it is denoted as this. Suppose, okay, for z, let's say, so suppose hg hz denotes the PDF. Okay, the PDF. And what happens is, what is h of 0? H of 0, what that means, when h can take the value 0, g can take the value 0. So g can take the value 0 when x is equal to 2. Okay, because the choices of x are like 0, 1, 2, 3, 4. So z or z equal to 0 only when x equal to 2. So then this will be nothing but f of 2, which is already known to us. So equal to 0, which is this, which is nothing but 6 by 16. Now suppose h of 1, for what values of x we can have this, this can be 1 if you take, let's say, x equal to 1, if you take, so 1 minus 2 squared is 1. And if you take x equal to 3, then also it is equal to 1. So h of 1 will be nothing but h of 1, f of 1 plus f of 3. So which is 4 by 16 plus 4 by 16, which is 8 by 16. Similarly, h of 4, so this can take the value 4. This z can take the value 4 when x equal to 0 here, x equal to 0, or x equal to 4. Okay, then z can take the value 4. So then h of 4 will be nothing but f of 0 plus f of 4. So this will be 1 by 16 plus 1 by 16, which is equal to 2 by 16. So then we can form Sorry guys, I think internet was gone. So just the notes is getting problem. Just a minute. I think now it will open. Yeah. So uh, yeah. So we can find out that h of 4 will be nothing but f of 0, f of 0 plus f of 4, and this will be 2 by 16. So we can find out the probability PDF of this random variable z, which need not be 1, 1. So like here, x minus 2 whole square. Okay, now I will give a rule, which is a theorem. So this is the for the continuous random variable case. Okay, so for continuous random variable case, the rule is, okay, so I'll just tell you the theorem. So here we'll assume that when we are given a function y is equal to, let's say, u of x, so that means y is a function of u of x. So we'll assume that this function u is differentiable. So when it is a differentiable function and either increasing, okay, increasing or decreasing, then I mean increasing and decreasing for all values of x, for all values of x for which fx is not equal to 0, then what we'll do is from this we'll write x in terms of y. So let's say this function will be then y is equal to w of y, and then this will exist. This exists, and for all values of y, okay, for all y, and then we'll take a derivative to compute the PDF of x. So the rule is the following. So this is the theorem. Will not prove the theorem. Theorem is like, let fx be the PDF of a random variable x, okay, and if y, let's say y is equal to u of x, so let's say small y is differentiable, and let's say either increasing or decreasing for all values, okay, within the range of x, for which fx not equal to 0. Okay, then for these values of x, the equation y equal to ux can be uniquely solved for x, okay, to give x equal to w, a function of y, and for the corresponding y, for the corresponding y, the PDF of y is equal to ux, okay, is given by the following function. So this is just a formula, which is f of wy and then mod of w dash y. Okay, mod of this provided u dash x is not equal to 0, and elsewhere, like where u dash x equal to elsewhere, gy is equal to 0. So basically, what is given is you are asked to calculate PDF of this y, which is equal to function of x, and the PDF of x is given to you. So then what you have to do is you have to write x in terms of a function of y, and this is possible when this function u is differentiable, because here we are using differentiability. So differentiable and it is increasing, okay, or decreasing within the domain where fx is not equal to 0. Then this is the formula for finding the PDF of y. So let us see an example to make the point clear. So example, let's say suppose x is following exponential. So x is following exponential distribution. So that means fx is, let's say, sum e to the power something. So let us say it is by minus x when x is bigger than 0 and 0 otherwise. Okay, so this is the PDF of x which is given to us, and suppose the question is find PDF of a random variable y, which is called the square root of x. Okay, so first what we need to check is like y is equal to this. So then this is nothing but, okay, the relation between x and y, and it has a unique inverse. So x you can write in terms of y. So x is written as a y. So this is actually what we said, w of y. Okay, so this will define as w of a function of y, and then w dash y, because it is needed for the calculation of the PDF, seeing the formula. So gy will be like f of wy times mod of w dash y. So this will be dx dy, which is 2y. Okay, and therefore gy is nothing but e to the power minus y square, because it is f of wy, and w of y is nothing but y square, and this was e to the power minus x, so it will be this, but the case is y has to be positive, so this times mod of 2y, so this is nothing but 2y minus y square, and for y is bigger than 0 as per the theorem, okay, as a statement of the theorem. And for all values of y, otherwise gy is equal to 0. So yeah, so this is the PDF of y. This is just the direct application of the theorem. Okay. Another way to look at, let's say, suppose it is not increasing, then what will happen? Okay. So suppose it is not increasing, but still I want to make use of this theorem. Okay. So So this theorem we cannot use if it is, let's say, neither increasing nor decreasing. But sometimes we can have a bypass this theorem, making a trick. Okay, for example, let's say, suppose this example. Okay, let's say x, let x be a random variable, and it follows standard normal. Okay, standard normal. Okay, and then find, the question is find the PDF of say random variable z, which is equal to x square. Now, see in the here the function z, okay, which is a function of x. So this is ux here. So which is x square, but this x square function, this is increasing, or let's say this is decreasing. This is decreasing when the small x is less than 0, and this is increasing when x is bigger than 0. So the problem is, let's say, okay, the problem is we cannot use directly the theorem 1, the formula, to calculate the PDF of z. Okay, so what we'll do in order to make use of the theorem, what we'll do is we'll do two things. So first we'll use a trick here. Let's say first we find PDF of, let's say, new random variable y, which is mod x, and then find PDF of z, which is equal to, let's say, y square, and y square is nothing but x square here. So mod x is nothing but, for now mod x now, which is because it is positive. So this density, this function is now increasing. Okay, so yeah, so we make use of these two facts together. Okay, we already have seen what happens in the previous example. What is the distribution PDF of y? Okay, when x is a random variable. So in fact, we have calculated that. So we have seen before. That fy is nothing but 2 times n y 0 1. So 0 is the mean and 1 is the standard deviation, mu and sigma. So if we just directly write this, it will be 2 by square root of 2 pi e to the power half y square when y is bigger than 0, and okay, instead of f, let me write it as z, and gy equal to 0 otherwise. Now we have to find out the PDF of, now then the task is to find, to find a PDF of z, or z. Okay, and the z or z is equal to nothing but y square, okay, which is increasing when y is bigger than 0. So and for which you see gy is not equal to 0. So this follows from, if I want to apply this theorem, we have to see that it was written that when all range of x, when this is not equal to 0. So here this fx is nothing but gy. So this fact we have to use. So then what will happen is, then again we can write it is like y is equal to fz, y is equal to square root of z, and then we can say dy dz is equal to a dz is equal to half z minus half, right? So 1 by 2 root z. So therefore we can say h of z is nothing but f of this. So f here is nothing but f of wy, if you can remember. So here it is gy. So f of gy times mod of the derivative w dash to y. Okay, so let us write, let us just use the formula, and then it will be f of 0 will be nothing but 2 pi e to the power minus half z, and then mod of half z to the power 1 by 2. So then ultimately it will give us 1 by square root of 2 pi z to the power minus half e to the power minus half z for z bigger than 0, and otherwise it is 0. And HC is equal to 0 otherwise. So in fact, here you can just see that this is nothing but, we just said before, this is nothing but chi-square distribution with the gamma value of number of degrees of freedom will be equal to 1. Okay, so this is just observation. So observe that this is chi-square distribution. So we proved that before actually. I mean, that was like x minus something whole square. We proved it. So observe that this is the chi-square distribution with the number of degrees of freedom gamma is equal to, let's say, 1. Now we'll talk about transformation. So this is the rule for transformation. So the two things you need to remember here. If the PDF of x is known and you want to find out the PDF of y, just we have to check that u is differentiable and either it is increasing or decreasing when fx is not equal to 0. Okay, now if that is the thing which is, then directly you can apply this theorem, and if it is not the case, suppose u is not increasing or decreasing, then you have to a little bit use a trick to make use of this theorem. Okay, so like actually what we did is we write this u in terms of composition of two functions, but forget about that. So the thing is, I want to implement u in terms of composition of this kind of function, increasing or decreasing function, and then individually on each of these functions we can use this theorem. This is the trick. Now let us say we want to do it for transformation of transform the technique for several variables. So more than one variable, let's say 2 variables. So this be now transformation technique for more than, so let's say 2 variable or 2 random variables. Okay, so here what we are given is we have 2 random variables, let's say x1 and x2, and suppose x1 and x2, and then suppose I am given a function y which is u of x1 and x2, or it could be a pair y1 y2 which is equal to u of x1 x2. Okay, so depending on what kind of function is a 2 variable function, 1 variable function, depending on that, okay, we can find it out. So if it is a single variable function like y is equal to u of x1, so it's a scalar valued function, let's say x1 plus x2 kind of a thing, okay, or x1 plus x2, then we have to see if this is the case. Okay, so then if we have to observe this, so if the, so basically the thing is, since it will be one variable, so we can use the theorem for one random variable and we can still compute the PDF of this y. So if the relationship between y and x1, okay, here x2 is constant, let's say x is constant, okay, or let's say we can also say between this or y and x2 when x1 is constant. Okay, so then we can proceed like x2 is constant, then we can find out the relation between y and x1. This is a function, then we can apply the single variable rule to find out theorem 1 basically. So then we can just say like g of y given x2, this x2 is given, so x2 is constant, so this will be f of x1 x2 times mod of del x1 del y, or we can say g of x1 y or y x1, whatever we write, so f of x1 x2 and del of x2 and del of y, and this yeah, so and this function f of xy is nothing but the PDF. Okay, and these are the partial derivatives. Okay, PDF of x1 and x2, and these are the partial derivatives. Okay, then we can compute this, let's say, marginal distribution of y. So because here, let's say x2 is fixed, here let's say x1 is fixed, and then we can find out the marginal distribution. So this is marginal distribution of y, you can find it out. So yeah, for example, okay, let us see an example. So let's say the joint PDF of x1 and x2, suppose it is given as this, fx1, fx2, which is e to the power minus x1 plus x2, when x1 is bigger than 0, x2 is bigger than 0, and let's say 0 otherwise. And suppose the question is, okay, find the PDF, okay, find the PDF of y, which is, let's say, some kind of like x1 and x1 plus x2. Okay, now see here, what is the relation between y and x1, let's say, when the other variable x2 is constant, okay, or relation between y and x1 when y and x2 when x1 is constant. Okay, that we have to see first. So now here, suppose x1 is constant, okay, then what will happen? Constant, then what will happen? What is the relation between this is x1 plus x2? So if x is constant, then see y is equal to nothing but some, this is some scalar, it's a fixed number, okay, this is some fixed number, so this is something by something plus x2. So it depends. So if y increases, let's say, or y decreases when x2 increases, okay, so we can find out using the transformation technique. So this is a one variable situation, like y is a function of x2 only, and the transformation technique, okay, we can find the joint density, okay, of x1 and y. So here y is equal to x1 by x1 plus x2. So this implies x2 is equal to x1 times 1 minus y by y. So then we can compute del x2 by del y, which will be minus x1 by y square. And then we can find the derivative, or maybe the x1 y. So we already got the derivative. And then the PDF, it will be nothing but, so because x1 was held constant, so it will be f of this times mod of minus x1 by, I'm just using the previous theorem. So x1, I think you have to give me 5 more minutes today. Otherwise I'll not be able to finish. I'm doing it quickly. So this one, when for x1 is bigger than 0 and 0 less than y less than 1. And then if I want to find out the PDF of y, okay, then what we can do is, then we can find the PDF of y by taking the value x1 0 to infinity fxt g x1 y here. So this is x1 by y square e to the power minus x1 times divided by this dx1, which is, so I'm just integrating it over x1 and then 0 to infinity. Okay. Okay, I have to make some transformation here. So let u is equal to some x1 by y. So this is u to the power minus u du, which is equal to nothing but some gamma 2, which is equal to 1. So this is how we can do it. And yeah, so we got the PDF of y. Same thing you can do, you could have done by observing the fact, like suppose x2 is constant, and then you see that how y depends on x2, x1, and if it is increasing or decreasing, then you can find out the joint distribution here, joint PDF here, and then you can again integrate it with respect to x2, and that's how we can do it. Now, finally, let's say, we talk about suppose x1 and x2 are two random variables whose PDF we know, and suppose y1 is a function, let's say u1 x1 x2, and let's say y y2 is a function u2 x1 x2, and now we want to find out let's say the joint PDF or the marginal PDF of find joint PDF or marginal PDF. Okay, marginal PDF of y1 and y2. So I mean, if we can find out the joint PDF, then of course we can find the marginal PDF. So this is how the theorem, this is the rule, this is transformation technique. So this is a theorem, and you have to understand this theorem. We are not going to prove it, but this is just an extension of the previous theorem, so it will be similar to that. Okay, so let f of x1 x2, okay, this be the joint PDF, okay, of the continuous. This is for the continuous case. So I mean, similar cases for the discrete. I mean, not this transformation technique, but putting the values of x1 and x2 in terms of y, and then you can calculate this. I mean, this is not a difficult thing. So anyway, so let this be the joint PDF of the continuous random variables. Let's say x1 and x2. Okay, and suppose these functions u1 and u2. Suppose the functions. Let's say y1, which is a function of x1, x2, and y2. So in the single variable case, this was differentiable, but here we'll call these are partial derivatives. So partial derivatives exist. So these are partially differentiable, okay, with respect to both x1 and x2, x1 and x2, okay, and yeah, and including the range of x1, x2. So this is not equal to 0. Okay, it's in the range of I mean, this is just an extension. So whatever the conditions are here, they are same condition here. So only the differentiation is replaced by partial differentiation. The range of x1 and x2, for which f of x1, x2 is not equal to 0. Okay. Then what we could do, like we did it for the previous case, single variable, we wrote y as a function of x. So here we'll write y1, y2 as a function of x1 and x2. Okay. Then the equations y1 is equal to u1, x1, x2. So x1 and x2 will be written in terms of y1 and y2 here. So one, then the equations and this, okay, x1, x2 can be uniquely solved for x1 and x2 to generate or to give let's say x1 as a function of, let's say, w1, y1, y2, and x2 as a function of y1 and y2. And for this y1 and y2, then the joint PDF is given by g. Let's say this function y1, y2 is nothing but the same thing, f of w1 here. Otherwise it was just wy. Here it is w1 y1 y2 comma w2 y1 y2 times the mod of j, and j is the Jacobian here. Mod means a determinant where j is the Jacobian of the transformation and here Jacobian is just the determinant of del x1 del y1 del x1 del y2 del x2 del y1 del x2 del y2 and elsewhere. Otherwise, that means when this is not equal to 0, I mean this is equal to 0, right? This guy is equal to 0. This f of xy is equal to 0. Okay, otherwise g of y1 y2 is equal to 0. So let us see. So an example. So let's see. Suppose okay, suppose here we have this. Let us consider this function only. So what is that? Yeah, this one. What is x1, x2 here? Yeah, this one. Let's say f of x1 is equal to this one, e to the power minus x1 plus x2. Okay. So suppose f of x1, this is given to us, f of x1, x2. Let's say it is e to the power minus what is that? X1 plus x2, I think. Anyway, so x1 bigger than 0, x2 bigger than 0, and 0 otherwise. So suppose this is the function what is given to us. PDF, which is going to be, and then the question is find the joint PDF of, let's say, y1 and y2. This is x1 plus x2. So this is u1 of x1 x2, and y2, this is, let's say, x1 by x1 plus x2. Okay, and then also you may be asked to find, let's say, some marginal. After you find the joint, you can be asked to find the, but anyway, you know the joint, then you can find out the marginal. Find also the marginal density of y2. So what we'll do, okay, what we'll do, okay, so here y is equal to, we'll just write x1 plus x2. So, and y is equal to x1 and x1 plus x2. So for first step will be to write x1 and x2 in terms of y1 and y2. So first we need to calculate the functions w1 and w2. Okay, so this is the first thing we have to do, and then we need to calculate the Jacobian. Okay, so then we can write x1 equal to y1 y2, and x2 will be equal to y1 times 1 minus y2, and then we can calculate Jacobian. You can say that it will be y2 y1 1 minus y2 minus y1, and which will be equal to this is the determinant, which is equal to minus y1. So therefore we'll say that g of y1 y2, this is the joint PDF y1 y2, this will be equal to e to the power minus y1 and mod of minus y1, so which will be equal to y1 to the power minus y1 when y1 will be bigger than 0 and 0 less than y2 less than 1, and otherwise g of y1 y2 is equal to 0. This is g of y1 y2 is equal to 0. And then if you want to find the marginal for marginal distribution, of course you know what it is, so but let me just write it. For marginal h of y2, let's see, want to find it. So 0 to infinity g of y1 y2, and then you have to take it with respect to y1, and you can find out the value. Okay, so whatever the value is, so that will be the marginal distribution. Okay, let us see one more example. This is the last example. Let's suppose f of x1 x2. So suppose this is defined as this 1 and 0 less than x1 less than 1, and 0 less than x2 less than 1, and 0 otherwise. And the question is find the joint PDF of let's say y1 and y2, or let's say just yz. Y1 is equal to x1 plus x2, and z equal to nothing but x itself. Okay, so then how will we proceed? We first write y is equal to x1 plus x2, and write z equal to x2, and then we have to write x1 and x2 in terms of y and z. So x1 will be equal to y minus z, and x2 is nothing but z. So once I get this transformation, this function is nothing but w1 yz, and this is w2 yz, and then we can calculate the Jacobian, which will be 1 minus 1 0, just the derivatives, okay, and 1, and then accordingly we'll say that therefore g of yz, which will be 1 times mod of 1, which is nothing but 1, when z is less than 1 less than z plus 1, and 0 less than z less than 1, and 0 elsewhere, and 0 otherwise. Okay, so this domain, this is coming from the domain of x1 and x2. So here x1 and x2, for example, here it is lying to 0 to 1, and then once you made this transformation here and here, let's say now x1 is lying between 0 to 1, that means z is lying between, and x2 is also lying between 0 to 1. Let's say z is lying between 0 to 1, and y is nothing but x1 plus z. So this is y is lying between z to z plus 1, because x is lying between 0 to 1. So that's how you can calculate the range of this. Okay. Yeah, I think now we have finished this. So thank you for your patience. And we had some problem today, the internet gone and that. Anyway, so if you have any quick question, you can ask me, and all the best for your exam. And we'll have the next class as usual, and we'll